In this final part, I'll give you one example of a field which on one hand is a very simple one. It has a finite number of elements and still satisfy every axiom of a field. On the other hand, it's very new to you. It's a very interesting complex example, in fact. But we have to start with some preliminaries, and that will be partial division theorem. Partial division theorem, something you know very well. Probably you don't know it in the form which I'm going to present to you first, but then I'll show you also the way you saw this theorem on numerous occasions during your school studies. So, in the mathematical form, partial division theorem sounds like this. Suppose we have an element n, which is an integer. Then, given that this element is fixed, for any integer a, there exists a number q, which is also integer, and a number r, which take only n different values, 0, 1, and all the way up to n take 1. And for these two numbers, so again, for any a from integers, you can find another integer q and another r, which takes only this finite number of values, such that this relation holds. So a equal n times q plus r. If you have such q and if you have such r, the number q is called partial quotient, and the number r is called remainder. That's the content of the partial division theorem. Sometimes, to reflect the fact that r is a remainder of a with respect to n, with respect to partial division with respect to n, people write like this: a triple bar equal r mod or modulo n. This symbol reads modulo n. Right, I'll give you one example, and then you will see the connection of this formal mathematical statement with the partial division method you know from this course, from the high school. So let me take a simple example of n being 5, right? So let n be 5, and let's just see this connection with the partial division theorem in the mathematical form and the way you get used to from your school. So if I take for instance number 7, here it is. Then I can represent 7 like this: 1 times 5 plus 2, which is true numerical identity, of course. But it looks like this, doesn't it? This looks exactly like this, with q being 1, that's my q, and r being 2. How did you find this representation? In school, normally you do like this. You take number 7, and then you divide number 7 by 5 partially. So you say, we put 1 in here, and then we subtract 1 times 5. So we subtract -5. The result becomes 2. That's all you do. And you call this your partial fraction, and you call this number 2 your remainder. That's how you did your partial division in high school, but in the proper mathematical terms, here it is. That's the way how it looks in the proper mathematical terms. Let me just do another one. For instance, number 9. For number 9, that's the representation. 1 times 5 plus 4. And again, I can do it in a school way. So here's my partial division. Here's my 9, here's my 5. Again, I put 1 in here. And now I subtract 1 times 5 from 9. The result obviously 4. And that's my remainder and partial quotient. It's a little bit more trickier when you go for the negatives. For instance, if you have a number -9, your first thought might be just put negative across this identity, so let's do something like this. but that's not really something you want to call a partial division theorem. The reason being is that here r is -4, and r, by the statement of the partial division theorem, must be non-negative number. Look at this. That's why the proper form of the partial division for -9, in fact, here, -2 plus times 5 equal 1. And so the remainder of -9 with respect to number 5 is 1, in fact. Now, if I use this modulo notation for these three examples above here, then I have 7 equal 2 modulo 5, 9 equal 4 modulo 5, and -9 equal 1 modulo 5. Right, now after we discuss with you what partial division theorem is, we can look at this very simple on one hand, but very interesting example of the finite field Z5. So I'll scroll it up and we'll just look at the finite field Z sub 5. So constructively, this is a very simple object. So the field Z5 is just the first, these 5 numbers, 0, 1, 2, 3, 4. Now, if I want to see that this is a field, in a way we discussed with you fields in the previous video, where we discussed the axioms of fields, I have to take 2 elements from my field. There isn't much of a choice to choose these elements, A and B. In fact, if you know a little bit of combinatorics, you would say that we have only 25 possible combinations. And I have to define for you what will be the addition and multiplication of these 2 elements. Of course, I can't take just a regular multiplication or addition because, for instance, if you take 3 plus 4, the result is 7, which doesn't fall within this set of numbers. So the normal addition is not something you want to take. So what mathematicians do, they take this 7 and then they take the remainder of the 7 with respect to number 5, which is 2. And so they say the sum of these two will be just 2 within this field. So formally, this defined like this. The sum of 2 elements, A plus B, in this field will be the normal numerical sum, but then we take the remainder of this sum with respect to number 5. And the same goes about multiplication. We multiply 2 numbers and then we take the remainder of this result with respect to number 5. Now I use this symbol plus in a circle, and I use the symbol times in a circle to distinguish this plus and times from the regular plus and times. This is a very unconventional way to write addition in this field because, in fact, in modern mathematics, this plus in a circle and times in a circle, they carry completely different meaning. But because we just in the first year, and you certainly not gonna deal with that concept, we save here. But so I use these symbols for now. But like I said, generally these symbols in higher mathematics they reserve for some other objects. And let's just see some examples. For instance, here's my example. If I take 3 plus, the plus meaning the plus of this set 3, we know we have to do the plus first. Normal numerical plus, which give us 7, and we know that the remainder of 7 with respect to 5 is 2, so the result is 2. If I do, for instance, multiplication of this field, that's the way it is defined. So that's the way it is defined. So first I do normal multiplication of 3 and 3. We know the result is 9, but we further out above on the screen above, we computed that the remainder of 9 with respect to 5 is 4. And so the result will be 4. Normally what we can do now, we can just build up these special tables. For instance, we can build the addition table here. We can build the multiplication table. For instance, now we know that if I go for the element 3 and I go for the element 4 here, the sum of these two within my field. We just discovered this. This is here. It's 2. So I can put here 2. Similarly, if I go, for instance, element 3 here and element 3 here, we just discovered that the product of these two, here it is, the result of this product is 4. So in the intersection cell, I put 4. Well, like I mentioned before, because our field Z5, and that's, well, we'll discuss why it is a field a bit in a second, but because it has only 5 elements, all possible combinations of sums and products will have only 25 possible combinations. That's why we have a table of 25 elements. You can do this computation for each of possible pair of A and B from Z. For every possible pair of A and B from Z, you can fill up these tables. Just uncover these tables for you right away. So here's the addition table, and here's the multiplication table. Now, of course, the claim here goes that this set Z5 with such defined addition and multiplication is a field. Is a field the way we defined field in the video before. And to check that statement, of course, we have to check every axiom on that slide or in that video, that these operations satisfy those axioms. Generally, this is relatively simple procedure. For instance, commutativity means, like, for instance, if I take 1 and I add it to 2, the result will be 3. And if I do the other way around, if I take 2 and I add it to 1, the result also will be 3. That's it. That's a commutativity check for the pair 1 and 2. The same can be done for the product, for instance. Associativity, existence of 0, which is just a regular 0 here, existence of unity, which is our numerical unity. All of this is relatively simple. What is a little bit more advanced is the existence of the multiplicative inverse, or simply the inverse. Let's just look into this. So what I claim here, let me just scroll it up a little bit more. What I claim here is that Z5 is truly a field, the way we defined it before. And most of the axioms are very trivial thing to check. However, I want to look at the existence of the inverse for every element of Z5. And that's, remember, the inverse was something, this inverse. This is something which if I multiply my A with this something, the result will be 1. But 1, in the way we understand this multiplication in my Z5 field. In fact, this last line can also be written, given that I use this symbol for my multiplication. This last line can also be written like this. A times the times of my Z5 field of the inverse, which we yet have to demonstrate the existence of, equal to 1. Right, let's just look at this. This is relatively simple. For instance, look at if I go, for instance, element 1. What should I multiply 1 with in order to end up with 1? Well, obviously 1 is here. So in order to end up with 1 after multiplication, this 1 must be times with 1 again. So the inverse of 1, something quite expectable, the inverse of 1 is just 1. More interesting stuff happens when you look at number 2. What this number 2 must be factored with in order to end up with identity. Well, that's the identity. So the number 2 here must be factored with this 3 in order to end up identity. So the inverse of 2 is 3 within my Z5 field, of course. Well, the same story happens when you go for 3. This 3 must be multiplied with 2 to give the result 1, which means that 3 inverse is 2. And finally, if you look at number 4, this 4 should be multiplied with another 4 to end up with identity. So the inverse of 4 is 4, something very unexpected, huh? Something very unexpected. And that's why your Z5 is true, is a field. That's why my Z5 satisfies every axiom we mentioned before. Of course, the existence of the inverse is the hardest of all axioms. That's why I pay attention to this to this particular axiom. Other axioms, like I said, they simple, very simple to check. I think you will manage that easily, independently. Now, you can also think about the similar construction, but with the number 6. So when you take not the first 5 non-negative integers, but the first 6 non-negative integers from 0 up to 5, you can again construct the field by taking the operations multiplication and addition modulo 6 now, and you can see, you can try to check whether this new set of numbers will produce a field again. The answer to that will be that Z5 in fact satisfies every axiom of a field except the one with the inverse. So in fact Z6 satisfies every axiom of a field beside the existence of the multiplicative inverse, and that's why it is a ring but not a field.